Yeah, hello, myself Omkar Suslatkar. So today I will be presenting our work ViCTr with my fellow teammates. Yeah, why is it so crucial that we address the challenge in medical imaging today? Our research is driven by a few plain points. Number one, basically, first medical imaging data is incredibly valuable, but it is also scarce and highly sensitive. We face a significant hurdle in gathering a large and diverse data due to strict privacy regulations and the confidential nature of the patient information. This data is scarce. It is severely limits our ability to train the robust and generalizable machine learning models for the medical application. Second, when we do work with this data, we find certain pathologies such as liver cirrhosis are particularly difficult to synthesis. This is because these conditions can present in a highly complex and variable ways, making it challenging for existing methods to create a realistic and diverse synthetic examples that accurately captures their appearances. Third, the major technical limitations we have encountered is existing generative models often struggles with the anatomical fidelity. They may be able to create images that looks visually appealing, but frequently fail to reproduce a precise anatomical structure and relationship that are critical for clinical accuracy. This is significant drawback when our goal is to produce images that are medically meaningful. To bring us to a primary objective, which is need for an efficient pathological aware synthetic imaging solution, our work aimed to overcome this limitation by developing a method that not only generate a high quality images but also accurate model to specific pathology and maintain the anatomical correctness. This will help us to create a robust and reliable and clinical useful source of synthetic data for training and research. Moving on to the next slide. Yeah, so key contribution. Yeah, so let's move on our key contribution. This is what our approach makes unique and effective. We develop a novel framework that address the challenges we just discussed. Number one, our primitive contribution is a novel two-stage ViCTr framework. This framework is one of the core method that designed to efficiently generate a high-quality pathological aware synthetic images. It handles the complexity of the medical data in a structural way, which is essential for our result. To improve the accuracy, realism of our generated images, we incorporate a twice corrected rectified flow. This technique improves the help to significantly reduce sampling biases, ensuring that the synthetic data we create is more diverse and accurately presented the real data distribution, particularly to the complex scene pathologies. Another major contribution, our ability to achieve one-step sampling with high fidelity, which many diffusion models require a large number of steps, sometimes 50 or more, to generate a single image. Our method can produce a high quality image results in just a handful of steps, that is 4 or 5. This makes our approach for more efficient and practical for a real world application. This is also represent the first method to graded severity pathology aware MRI synthesis. This means we cannot only generate the images with a specific pathology but also can control the severity of the level of the condition, which is crucial features for the training to recognize and differentiate between the different stages of the disease. Finally, our method can direct measurable impact, where we can able to show that our synthetic data is like for the augmentation, improve the segmentation by 3.8% in MDICE or mean dice similarity. This is significant performance boost that demonstrate a real world values of our generated data to improve the accuracy of the clinical tools. Yeah. Now, what are the existing? Now let's discuss what are the existing works previously have done. So there were few techniques which are the GAN based, that is a style GAN for the medical imaging. There are few diffusion models like MedDef or MedFusion, and there are like a lot of previously generated diffusion based techniques which are using the DDPM. But there are very less exploratory fields in the rectified flow or the flow matching. Yeah. To provide more detailed understanding of our methodology, let's look at the technical foundation rectified flow, which serve as a baseline. Rectified flow is a generative model that operates by learning a deterministic velocity. Here xt represents the image at the time t, and v theta is the velocity field learned by our neural network, basically parameterized neural network. For formulation, facilitates smoother and more direct trajectories between the noise and the manifold, which is significant advantage over the stochastic process. However, a critical issue arises when the applying to this to the medical data. Despite benefit, the standard rectified flow is still susceptible in the sampling biases, particularly when the dealing with the inherent noise and the complex distribution of the medical images. This basis limits the model's ability to accurate synthesize and rare or sustainable pathologies, which is key challenge we aim to overcome with our proposed Twedis formulation. Twedis correction and our contribution. So our method introduces a Twedis correction to the rectified flow process. This is designed to counter inherent and sampling biases in existing method, especially when dealing with the noisy and more complex medical data. Posterior adjustment. So basically, this is one of the main reason why we are using the Twedis correction. The core idea is to adjust our model to estimated of the mean flow of the data distribution, which is represented as mu theta by the z, by adding a term that accounts for a logarithmic of the probability density of the data. This is a technical step that essentially pulls the model's prediction closer to the true and unlined data distribution, even when the initial data is noisy. Integration of the flow. This correction is integrated directly into the flow ordinary differential equation, that is SD or OD. This modifies the velocity field equation to incorporate the Twedis correction term. The modified equation now guides the image generation process not only towards the target image, but also towards the most probable part of the data distribution, which helps ensure the anatomical and pathological accuracy. Our main also we have discussed previously that one of the contribution is the distillation and the single step prediction. So the final and most impactful technical contribution is ability to distill the entire complex process into a single step predictor. This means that instead of running the models for over many time steps to generate a final image, we can predict the final image directly from the starting noise. This makes our model significantly more efficient and more faster and more differentiable, because the sampling process is non-differentiable, and for multi-step process to a single step. Yeah. Now let's discuss our framework, and the following figure represents our framework, that is ViCTr. So for training this network, we have used the Flux as a base architecture, and we can see from the clearly in the figure that only the trainable parameters are here are only the output, basically output attention layer of the Flux and the hinge layer basically. So from the EWC, basically the elastic weight consolidation, we have seen that like for what basically while training, what are the most parameters while updating, what are the most crucial parameters which are help to updating the model. So those parameters are only we are updating, and rest all the parameters we are freezing. So approximately we are only updating nearly about 2.5 million parameters of the entire Flux method. Yeah, so this is the pre-training stage. Why we are need to do the pre-training stage? Because one of the main reason is like Flux, basically the Flux image generated model is only specifically trained on the natural scene images instead of the medical or specific to the medical data. So to train with our specific medical data, we have trained our model with 100 near about 1.3 million scan images with the guidance of the segmentation map. Yeah, and if you now we are going on the stage 3. So this is our entire ViCTr framework. So in which we are in which there will be our base model, which is the pre-trained model, and there will be the adapt model basically. So adapt model will learn the adapt model will learn the new modality, basically new modalities inside the medical imaging, and it should not get to the mode collapse. So that's why we are also adding the KL divergence between the base model and to the adapt model, so that it should not move too far from the base model. So this is our entire framework for the fine tuning, that is the ViCTr stage 2. Yeah, so now we are going to the experimental setup. So there are the basic experimental setup we did. So in the stage 1, that is the pre-training, we use the Atlas 8K dataset, which is the CT scan with the segmentation mask. In stage 2, this is the fine tuning. So we did with the fine tuning with the BTCV, basically the multi-organ synthetic dataset, AMOS, MRI abdominal dataset, then SEER MRI 600 plus, T1, T2 MRIs, liver cirrhosis with the graded severity. And evaluation protocols, we are doing FID, then MDICE and MHD95 for the specific segment to get the segmentation improvement. Also, we have also introduced a new metric, that is the MFID, which is specifically for the medical imaging to evaluate the performance, the generated performance with the medical images, that is MFID. Yeah. So from the results, we can clearly see that if we have trained our ViCTr with the different baseline, that is stable diffusion XL, stable diffusion 3, Pixart alpha, and the flux. And we have seen that like flux has the best MFID as well as the FID score throughout all the variations. Even in the CT, even in the CT generation, even in the MRI generation from the AMOS dataset, or even the pathology generation from the cirrhotic 600 plus dataset. Yeah. Qualitative results on the segmentation. So now what we did actually to get our generated data to have the meaningful to use in the meaningful conditions. So we generate the segmentation. Basically, we generate a lot of segmentation images for particularly for the BTCV dataset, AMOS dataset, and the cirrhosis dataset, and we train the few methods, that is NN-Former and MedSegDef, and we check and we validate that, and we compare and validate that our data augmentation, basically the synthetic data generated from our method, is more augmented than the previous augmentation techniques, like or the traditional augmentation techniques, and we can able to get a pretty boost in the segmentation performance. We have also did the alignment study between the ground truth distribution and the generated distribution, and with the other techniques, and we can clearly see that the ViCTr can able to overlap the ground truth distribution very closely than other previous distributions. You can also clearly see that the qualitative results on the pathology generated images, in which we also did the severity control, and in generated cirrhotic liver, we can able to see that the texture and the patterns are clearly visible by our method. We also did the qualitative evaluation based on the CT and MRI generation. So this is basically like the semantic guided CT generation and the semantic guided MRI generation. From this, we have also seen that like our method, when we are using the flux as a baseline, it can able to synthesize more accurately generated images. It can also able to handle the variational divergence to the edges and the boundaries. Conclusion. So basically, we in the conclusion, I just wanted to say that like we have introduced the ViCTr as a new method for the medical image synthesis, combining with the rectified flow with the Twedis correction to reduce the inductive bias and enable fast one-step sampling. Preserve anatomical fidelity with the generating clinically realistic pathologies, outperform baselines in FID, MFID, MDICE, and HD95. Offer a scalable framework for synthetic medical image generation, support research, training, and clinical applications. Yeah, thank you, and you can scan the scan the QR code here for our models and for the model and the code. Thank you.